Hello again, welcome to another episode of programming course. At the last session, we have been tried functions and we tried to find a number between 0 and 100,000 which must be prime and perfect at the same time. We searched and nothing has been found, and I hope you have searched and found the such number. Uh, actually, in this episode, I tend to talk more about the functions and what they do and what they could do and what is the meaning of using them and something like that. We're not going to take it that hard or that easy, something in the middle, which could be a fair step to um, this course. You're not going too much of information, you're not going to learn nothing. It's something in the middle. Just don't worry and follow up. And of course, you have to make it yourself. You have to write it, you have to watch it when it runs on your computer, and you must feel the result in the tip of your fingers, because as a wise man said once, the hard works will beat the talent if the talent fails to work hard. So you have to work hard despite your talent. So let's just jump right in, and I'm going to write a function which I'm going to call it get name, like this. You could use anything, and my function, I want to pass 0 parameter to it, so it's going to has no argument or no input, so it only has an empty parenthesis. So at this point we can understand that the function could have 0 or more argument. I could just tell it has a b c d or whatever argument that it needs to, so it's going to have 1, 2, 3 or more input or argument, but for this function I just want to call this, and the function gives me the name of the person that is using this program. But how? I want to print a prompt that says enter your name and gets the name and returns the value. So I can just say that the name is equal to an input function that we have already discussed. It accepts a prompt. I'm going to say please enter your name and a colon, and whatever the name is, I'm just going to return it. So that's my function with no input. So if I want to use it, I can just say the person is get name with the parentheses and no input, and then print hello and the person name. So if I run this, it says enter your name, and I want to write my actual name, which is Siavosh, and it says hello Siavosh. So that is quite simple, isn't it? What about we want to write a function for this part? I'm going to write it as greeting, and it gets a name and prints the hello plus the name. So I can just get the name and call the greeting with this person thingy. So I'm going to clear this, and if I write this and type my name, it says again hello Siavush, which is expected but through the functions. And I can just combine these functions and pass a function for the argument of another function. So if I just run this, it's going to work just like before with zero changes, because that is what we have done, but we have lost the person value, and if we need to do anything with the name of the user, we have to ask it again because we haven't saved it anywhere. We have no variable which could represent the name of the user. So that's the reason we can use the variables or not. But in this case, I just wanted to say hello to the user, so there is no need to save the name somewhere in the memory, so we don't need any variable. So let's do another thing. And from the school that you can do multiplication if we can just understand how addition works. For example, if you want to multiply 5 by 2, you can just write 5 twos, 1, 2, 3, 4, 5, and just add them together. Add just some pluses, and the result is now equal. So I want to do it but in Python. So I'm going to define a function. I'm going to call it mul, which represents multiplication, and gets to number n1 and n2, number 1 and number 2, and any summation must have a result. So I'm going to just call it result, which is 0 at the beginning. It must be something at the first, and we're going to add the number to the result, so it couldn't be just result out of nowhere. So I initiated the result with the value of 0, and I'm going to add n2 to results n1 times. So I need a for loop which the index must be in range of number 1, and at any iteration it's just going to add it up with number 2, and the result is going to be the number result. So I'm going to return the result variable. That is the function, and the I is not used anywhere because we don't need this. We just want to do something n1 times. For example, if I wanted to this example, it's going to be mul of 5 and 2. So 5 is n1, and range of n1 means 5 times. So we're going to add number 2, which in this case is 2, n1 times, which means 5 times, with something we call result, which is 0 at the beginning. So eventually we are going to add 2 5 times to itself, and we reserve it somewhere at the result variable. So let's see if it is working or not. I'm just going to print multiplications of 5 and 2. Yet the result is 10, and this is working. What about multiplying in 0, which is already working, because you can add up many zeros together and the result is again 0. 5 and 3, yeah, 15. This is working like a charm. So you can do anything with these functions, and the functions are kind of mini programs that you can use it in your real big large program. And of course you can write many functions and make them a library. We are going to talk about them later, about the libraries and stuff, but right now let's write another function for the power. If you want to increase a number by a factor of 2, 3 or something, you need to use the power, but the power operation is not directly accessible in Python. You have to import something called mathematics like this, math, and from math, let's just comment this for a moment. You can just print from math power of 2 and 3, which could be in result of 8. Yeah, this is 8, because 2 to the power of 3 is equal to 8. It means that you are multiplying 2 3 times, which could be the 8 itself. But the power function is not natively accessible. You have to import a library called math to do it. You can just use sqrt for a square root of. It is going to give you 2 if you give it 4, or it could be 3 if you give it 9, and this is square root of anything. For 3 it's not a whole number, so we can just see what is going on. But without this math, this is not going to work, because we don't have the power natively. So let's just make it power natively. You kind of need 2 arguments, because you need a base and you need a power, so you have to get those 2. And just like before, you can just reserve something called result, but instead of adding, you have to multiply it by n2. So if I again add I write power of 2 and 3, it says 0. Why is it? The result is 0, and 0 times anything which results to 0. I just need to change the initiative value of result to 1. So yep, 2 to the power of 3 is 9. No, actually this is 3 to the power of 2. So I need to swap those. This is going to be n2 and this is going to be n1. Yep, that is great. 8. What about 5 to the power of 10 or 100? It is a large number, but it is a number. And the power of 2, which could be 25, which it is 25. And this is kind of this seems easy. What about the power of 5 to the power of multiplication of 2 to 5, which means 10, and 5 to the power of 10, it could be a large number, which it is. So you can just combine those functions together and create something more complex with them. So let's just get rid of it for a second, and I'm going to introduce you to a sequence that is known as Fibonacci sequence. And in this sequence, two first elements are 1, but from that point, which means the third element and so on, it's going to be an addition of the last two elements. For example, the element 3 is equal to element 2 plus element 1, which in this case are 1 and 1. If you add them up, it's going to be 2. And the fourth is going to be 2 plus 1, which is 3, and 5, 8, and so on, 13, and then 21, 52, no, 34, yeah, and then 55, 89, and so on. I'm not going to add them up. This is what we call it a Fibonacci sequence. Yeah, this is a Fibonacci sequence, and let's write a function for this Fibonacci sequence. I'm going to tell this, let's just make it a bit easier. Let's write a program that calculates first 10 elements of the Fibonacci sequence. So, we know that the first elements, I'm calling it Fib1, is 1, and Fib2 is 2. But Fib3, at the other hand, is Fib1 plus Fib2. So after an iteration, I have to swap those. So the Fibonacci 2, the Fibonacci 1 is not the 1 itself, it's going to be this one. I have to consider this for the beginning of my subsequence to calculate the third. Let's do it by code. That could be a bit easier. So for I in range of set 15, whatever, doesn't really matter, I'm going to calculate this part. Yeah, that's it. And then I'm going to swap those so that the Fib2 is equal to Fib3, and Fib1 is equal to Fib2. I hope I haven't screwed this, and the result is at the Fib, let's just print this. Print Fib3 and a comma. So let's clear this up, and if I run this, I have to disable this ending thingy. It starts with 3 5s. Yeah, the 3 5 8 13 21, whatever it is, this is true, but the first elements are missing, and the reason is we start with Fib3, and the Fib3 is equal to this, and what is it, 2 plus 2, oh, that must be 1. I went one step ahead. Well, no, just run this. Yeah, 2 3 5, yeah, that makes sense. And we have got rid of this Fib thingies here, that's okay, because we haven't mentioned the print for those. The print is inside the for loop, and whatever happens inside the for loop, it's going to return that. So I can increase this for 100 sentences. It goes to, the 100th element of this sequence would be a large number. So let's make this a function. I'm going to def, fib, whatever, and an indicator, we call it n, which goes to be the nth number of the Fibonacci sequences. So I know that if the nth is less than or equal to 2, the second number and the first number and whatever it is, the result is 1. But otherwise I have to go through it nth time minus 2, because we have these two first elements pre-calculated. I have them from before, and after we have went all the way at this Fibonacci sequence, I'm going to return the value, which is the fib3 in this case. So I can just say print Fibonacci of 1, and let's copy this 2, 3, 4, and if I run this, it's going to be 1, 1, 2, 3, which is 1, 1, 2, 3. Yeah, that is completely true. What about 5, 6, 7, 1, 1, 2, 3, 5, 8, 13. Yeah, this is completely true, and I can just write a for loop outside the function itself for I in range of, you say, about 20. Just print the Fibonacci of I, and the ending is a comma. So if I run this, that gives me the first 20 item of the Fibonacci sequence, but you might realize that there is 3 1 instead of 2 1 at this sequence, and the reason is the range returns 0 as the first element, so it's going to be 0 1 2 instead of 1 2. So I'm going to say that the range starts from 1, and if I do that, you see that we have the exact 2 1s in our sequence, so the Fibonacci sequence is actually correct. So if I ask this function to go all the way up to 2000, it's calculating as, like instantly. It doesn't waste any time. So, I'm going to introduce you to another topic. We call it the recursive functions. A recursive function is a function which calls itself inside itself. It's like something like the Inception movie, I believe, which they could fall asleep when they were already in a sleep. So it's going to be in a sleep inside a sleep, and there's going to be a function inside another function, which is itself. So let's write this function. I'm going to call it the fib_r, and stands for recursive, and the nth argument we have already knew, and this condition here, we know that the nth number, if it is less than 2 or equals to 2, the result would be 1. But what about the otherwise? The otherwise, which is else, it's going to be return the result of fib r of the previous element plus the fib r of the two steps behind. So in this point, if you want, for example, 21, you have to find 13 and 8 and sum these together to reach to 21. And this is all we have done here. If you want the nth, you find the nth minus 1 and you find the nth minus 2 and add them together just like that. So I can just get rid of this else part, because if this condition were true and we hit return, there is nothing to do for this function and kinda blocks the second instruction here, because as soon as you hit the return in function, the job of that function is done and it does nothing more. So going to back to 20, it works already, and instead of fib I'm going to use fib r, and if I run this, I can get the exact result as before, because that is a recursive type of Fibonacci, which gives me the exact result. I just wrote the rules. You have to find the previous and the previous from that and just add them together. That's the simple rule that I have written there instead of this kind of nonsense. But if the recursive functions are that easy, so why wouldn't we just use them anywhere? At the science of computing and the programming things that is more advanced, we are going to use recursive functions, but not anywhere. Not everywhere. That is because the recursive functions are not efficient enough. For example, at the previous example, if I wanted to print 2000 numbers, it just gives me instantly the result. But if I ask my new algorithm to find those, it kind of takes a while to give me the results, and because that is really slow, and the reason is it consumes a lot of memory. I'm not going to crash my computer in the middle of recording this, so I'm going to cancel that. Let's go with 100. Let's see if it can handle 100. It takes a while, but I haven't actually seen any result. Let's do another fair test and just simply print fib r of 100, only one element, and it's going to take something like, I don't know, but it goes out easily. What about the 50th element of this sequence? It is still struggles. The reason is that in recursive algorithms we need a lot of memories, uh, let me just show you an example of what I mean. So as you can see, it still struggles, but as it struggles, let me just explain what is happening. For instance, imagine that you want to find f. I'm just calling f for the the simplicity. I'm not going to write fib every time. Let's see that we want to get Fibonacci sequence of let's say the fifth element. It needs to calculate the Fibonacci of 4 and the Fibonacci the Fibonacci element of 3, I guess, and add them together. But for finding the Fibonacci of 4, it needs to it needs to kind of find the Fibonacci of 3 and and the Fibonacci of 2 and add them together. For the 3, it's kind of obvious for you at this moment. It needs to find the 2 and Fibonacci of 1 and add them together. But for 1, as you can see here, it's less than 2, so it doesn't need to find anything. It knows the answer is 1. I'm just going to cancel this. So it knows the answer is 1. It says, okay, this is 1 and this is 1 too. We just add them together, it's going to be 2. For this is 1 because this is 2 and less than 2. It fits in this condition. So this is 1, but for this I need to calculate the result of Fibonacci of 2 and the Fibonacci of 1 and add them together, and it knows that this is 1 and this is 1, so it goes all the way for 2, and 2 plus 1 it's going to be 3, and the 3 plus 2 is 5. What? No. It is 5. So the fifth element of the Fibonacci sequence is actually 5. Let's see, 1 2 3 4 5. Yeah, that is right. And this is how the recursive algorithm works. We call it the recursive tree. These kind of things that I have drawn here. And for each of these iteration, the CPU needs to go all the way and opens a new element and a new state of the memory. I'm not going to talk about the computation theory and how CPUs work, but there are a lot of function calls, and for every function call your CPU needs to save everything from that moment and that a snapshot of that moment, and save it somewhere at the inside the memory. And creating those snapshots, restoring them and calculating them is a lot of memory consuming a process. So the recursive functions are easy to write, but they are not efficient at runtime. And the reason it was struggling was that there are, for the fifth element we need 1, 2, 3, 4, 5, 6, 7, 8 function calls. But for the number 6 of the Fibonacci sequence, we need double that amount. For example, if we just wanted the fourth element of the Fibonacci sequence, we needed just that part of the tree. But for the 5, we need this extra thingy here. And for the 6, we just need a lot of things here. So it doubles off any time that you want to add a number. And for number 100, it's going to be 2 to the power of 100 system calls, which is a lot of system calls. And this is the reason why it is so slow, and it doesn't give me the answer. But in case of like 20, it can handles that and gives me the answer. But as soon as it passes that 20, goes to 30 or anything, it's going to struggle harder, because there are a lot of function calls, and the memory kinda it takes time. It's not something that is not doable. It is kind of doable. It is absolutely doable, but that is really time consuming, and that is the reason this is really slow. Because for any number that you increase, you double up that function calls, and this is the reason it is so slow, because eventually you're going to run out of memory, and the CPU kind of needs to write the information somewhere on the disk to not losing them. And the disk is really slow compared to memory, and the whole application kinda gets slow. So we try to avoid recursive functioning in those situations that we need a lot of system calls. Like in this Fibonacci sequence, we need to call double the amount that we have already been asked. If I ask for the Fibonacci of 3, for example, it's going to have 2 other system calls for those recursive functions. But in case of the non-recursive function, this is really fast, because there is no extra snapshots of the CPU at the moment, and we don't need a lot of memory. Just a bunch of variables would do it. So that is the reason that the recursive functions are not a priority for the productions that are really sensitive, and they need to be super efficient. But this is popular among the new learners, because this is really easy to write compared to this. But at the perspective of memory management, this is not efficient, and you should not use that except if you have to and you had no other chance. There are some situations that recursive functions are actually more used, and the reason is the amount of memory and the time that the recursive function needs fits to the non-recursive equivalent. And for some jobs, we have no other option instead of recursive function programming, and this is the point that you have no other chance. You have to kinda use the recursive functions for finding or for working on a graph and this is really advanced. I'm not going to talk about them. Let's postpone them to the time that is convenient. But right now, I just wanted you to introduce you to the functions that have no arguments, more than one argument, and the recursive functions. And I think the mission accomplished. And I sincerely ask you to do your practice. I don't care about your homework and stuff. If you do not do that or do that, it has nothing to do with me. But if you want to learn it, you have to kind of feel it in tip of your fingers. You have to write it yourself. You have to see the challenges that you are going to face with. I hope you enjoyed it. If you did, I would be happy if you leave a comment below. And until the next episode, bye bye. Take care.